So hi everyone, welcome back to the channel. Today something a little bit different. We're going to look at an example of crap engineering in the bike industry. This was a little project given to me a while ago by a friend of mine, and I thought, hey, why not, let's make a video about it. It's probably not something you see every day. It's kind of a weird fix to an old bike that you want to keep on the road, but it got me thinking about how lax the standards of engineering were in this particular part and this particular company at this time. I'm not saying this is exemplary of the current state because it's quite an old bike. It was pretty surprising and I decided to make a little video about it. Some of you might find it interesting, so if you haven't already, give us a like and subscribe and get involved in the comments. Helps me engage with you more. Anyway, let's dive into the PowerPoint and have a look. Right guys, so let's get into the PowerPoint now. Begin the show. Crap engineering, a case study, and this is based on a Look 496 TT bike, and it revolves around the stem arrangement, literally. You'll see why. I don't know what year the bike was made, but it's quite old. It's definitely over 10 years old. And if any of you know, let me know down below. I couldn't find much info about it on the internet. They made a track version, they made like a TT triathlon version, so this stem can also be found on the track version. Anyway, let's have a look. So it's an old bike, first of all, let's not be around the bush. It's pretty standard TT bike, also made a track bike version with different rear triangle with horizontal dropouts. And it has this particularly funny, let's turn the pointer on, stem arrangement on the front, which is 2 plates and a faceplate, normal faceplate, 4 bolts. And you can set the angle of it, you can adjust the height and angle of it with this central M8 pinch bolt. Okay. What I'm about to discuss, these aren't new engineering principles. They've been around pre-industrial revolution. They've been around since the Egyptian fucking times. It's not complicated. These principles are basic and they're not time dependent, they're not technology dependent. So in this case, this one will be quite harsh. It's inexcusable because it's a basic design flaw and it's not, you know, generation dependent, so it shouldn't be there. It's not as if the companies couldn't access this type of technology or this production method. It's not like that. It's just a very basic design problem. Quick look at the contents before we get into the meaty stuff. First of all, we're going to look at an example of a standard or basic engineering design process and sign-off, which encompasses the critical design review and everything. Now, I'm not saying this is good engineering or good practice. This is like basic. This is a very top-level, reduced down overview of what kind of process a very basic engineering company or anything making anything should go through. It's actually more elaborate than what I tell you, but I've had to, you know, slim it down. Then we're going to have a quick look at the evaluation of the failure and actually what happened to this stem. Was the failure mode, which we see here, which we will see here, considered in the design process? Well, I can skip to that answer now, and it's no. What was inherently wrong in the design? Was it flawed? We'll come to that. Number 5, more dipshittery from the manufacturer. We'll come to that. What we did to fix it. Okay, so I mentioned about a basic procedure in engineering, which is called design process and sign-off. This should happen in any company that makes a product that goes to market. If they're responsible for the design and manufacture, even if the design and manufacture is outsourced somewhat, the company should do a basic process like this. I've shrunk it down to 5 kind of steps to keep it brief, but actually in most engineering firms it's kind of more elaborate than this. But anyway, step 1. The junior engineer or design engineer conceives a design concept. He might sketch it, might do it on 3D CAD, all depends. Then he'll draw the piece parts, which are the individual components, the sub-assemblies, and maybe a kind of more top-level assembly to show how these parts fit together. Forms a bill of materials, that might be bolts, nuts, bearings, things like that, including standard bought-out parts, bearings, springs, washers, circlips, that sort of thing. He then passes this whole pack of drawings with all the piece parts and the sub-assembly drawings to a colleague for basically peer review, or a group of colleagues, and they'll perform a critical design review. This is a basic process, happens in most companies. The peers then, they genuinely, like senior peers, they will assess the designs, they'll talk to the designer and maybe make suggestions, maybe make changes. Things like, can we use less material, can we make it lighter, can we make it cheaper? Is it even possible for the machinist to make it? Can tolerances be looser to make it cheaper? Can coatings, finishes, materials change to make it cheaper or better? And all those comments are taken on board by the designer. And the designer in step 3 here may rework the drawings or rework the designs to apply those changes based on the critical design review. The designer will then pass those reworked drawings and that drawing pack back to the same guy or the same group of guys or girls that did the peer review on the critical design review in the first place. So there's consistency there, and that's important. So the reworks are then checked by the critical design review, and then if the senior colleague is happy with it, he or she will sign off the drawing pack and bill of materials for manufacture and purchasing. And then in the case of like quite high level civil and like civil engineering, automotive, aerospace, if that senior colleague is chartered, they are now legally responsible for that part in use. And that legal responsibility gives a level of, fuck me, this better be correct because my name's on this, my neck's on the line. And that's the important bit about this whole process, is this number 6 part sign off. That guy, for his reputation, needs to know that all these steps have been covered, he needs to know the design's going to work, he needs to know it's not going to break, and he's going to have done something called failure mode and effect analysis. So, I am 99% certain that when Look designed this part of the bike, or when they designed the whole bike, they didn't do that standard process that I just mentioned on the previous slide. Or if they did, the senior guy or girl wasn't really a qualified engineer. And I expect that's what happened. So let's have a quick look at what actually happened to the woeful design. So this is the stem in question, right? It has 2 plates which pinch the bike frame via a single M8 pinch bolt. It's got a standard faceplate that holds the handlebars on, and the M8 bolt loads the part through here. One of them is threaded, one of them's got a through hole, and the user does the M8 bolt up to set the angle of the stem to the desired angle. It's pretty nice, yeah, why not? Set the height and angle of the stem, and then the friction between the clamped faces against the central portion of the bike stops the stem rotating. And now I'll let you make your own mind up as if that's a good idea or not. And yeah, it snapped under the tensile loading of the bolt. It snapped right here, and this part used to be attached to this part, and the tensile loading of the bolt just ripped that part off. Now we'll come to why it did that in a minute. How did this happen? The user experienced slippage of the stem angle. He then put up with it for many years. Like I said, he's had this bike for years. It's an old bike. He didn't really ride it that much. It sat in front of the TV and he used it on the turbo. He constantly tried to tighten up the pinch bolt to increase the clamping load, as you would, because you don't want it slipping whilst you're riding it. Finally, the stem broke under the tensile loading of the bolt, and this tensile fracture happened. Now, luckily, he didn't injure himself, but he was riding outside when this happened, and like, they only can imagine the injury he might have sustained if he was unlucky. Like, face into the front wheel, face in the tarmac, teeth out, blood everywhere, fucking spokes in your nose. Really, really, really dangerous. A really shit design to do it like this. And I was quite shocked that actually it was designed like this and he wanted me to fix it. So, I mentioned something called failure modes and effects analysis. Was this failure mode considered in the design process? Absolutely not. I can't believe it was. And what makes this so bad is that probably only 2 real bad failure modes in the FMEA process, in the table. One is the stem slipping, which is kind of not a failure mode, but it's a problem. And the other failure mode is the stem snapping under the tensile loading of the bolt. And that goes for kind of any bolted component. That's always a potential failure. But what's particularly bad in this case is that Look, the manufacturer, made those 2 failure modes extremely likely to happen, which is just like a complete shambles. So it's like it's like you're on a ski slope and you know there might be an avalanche, and they just go and throw a stick of dynamite on it, and it's just so anyway. And if you want to know what failure mode and effects analysis is, Google it, go onto images and look at like what a standard chart looks like, and it's how designers and people kind of evaluate the potential failures, and it helps drive design basically. Anyway, this is my reduced table, and it's containing something called a fuckwit score, and it shows you how bad this design is, because both failure modes are severe and they're extremely likely. So in total, this is 90% shit, in my opinion, because they made them extremely likely and there's no redundancy in there. Yeah, I won't mention it again. The flaws, well, I've gone through most of them already. There's only one single pinch bolt to fix the stem and set the angle. Now, if there's only one bolt, it's just a pivot. If the friction, if the clamping friction isn't enough, it'll just pivot around that bolt, and it'll be going up and down, and be extremely dangerous. And yeah, there's no anti-rotation. Now, anti-rotation would be a pin, a keyway, some sort of feature to stop the thing moving up and down once it's slipped, dowel pins, something like that, or just another bolt, like another bolt somewhere. It's baffling how this came to be. There's no redundancy. If this bolt snaps, you're fucked. Your face is in the wheel on the floor. There's not even a second bolt. It's pretty bad. Over tightening to try and stop the slipping, which will happen, causes bolt failure or tensile failure of the stem. And there wasn't even any like fillets or radiuses under the bolt head in the corners. And actually, at corners, technically, theoretically, the stress is infinitely high, because it's a singularity, it's a single point. The stress in that area goes to infinity. And yeah, I couldn't believe there wasn't even a radius under that part which was being loaded, but I'll show you that in the drawing in a minute. It's bloody heavy. That's like the least thing we can worry about at the moment. You know, it's just a very thick plate of aluminium. There's no webbing, there's no like shelling on there. It was heavy and it's crude. Another criminal act, the bar opening diameter of the clamp, of the stem, where it clamps, is less than the diameter of the bar. So what does that do? Well, the corners, when you put the bar in, you put the bar in the stem, the corners pinch, the corners pinch the bar. And if you're using a carbon bar, that is the worst possible thing to happen. It'll just damage the handlebar. When you clamp up, it'll just, those corners will just push into the side of the bar. Anyway, we'll get to the diagram of that if you don't know what I mean. Number 7, flawed UX. Another thing, if the user does the handlebar bolts up on the faceplate first, the slipping of the stem may be even worse, and I'll come to that in a minute. But going back to the one single pinch bolt to fix the stem rotation, they might have done, let's give them benefit of the doubt, they might have done a bit of like bolt load calculation on friction coefficients and torque and everything. But let's not forget, when you're riding over bumps and potholes and stuff, you get instantaneous G-force. And let's say you're on this is on a TT bike. Let's say you're 80 kilos, right? Let's say weight distribution on the saddle and on the handlebars for your elbows is 50-50. So 40 kilos on the saddle, 40 kilos going down on the bars. Let's say you hit a pothole, there's instantaneous acceleration of 3G. Your 40 kilos on the handlebars becomes 120 kilos. That's 1200 newtons. Let's say the stem is 150 mil long. 1200 times 0.15, 180 newton meters of torque trying to rotate the stem. And that's a shitload of torque. I'm not lying. Alright? So, yeah, it's a criminal. I can't believe they ever got away with that. Or I wonder if they ever tested it up to 180 newton meters trying to rotate it, because that's a lot. I'm not saying it slips in every scenario. When you're riding along, it probably won't slip. But if you hit 3G or even 2G, 2G is going to be, you know, still a hell of a lot of torque trying to rotate the bar. I wonder if they ever did the calc. Anyway, let's move on. Let's look at points 6 and 7, which I briefly spoke about. And these would be criminal in their own right, but in the context of the whole thing, actually pretty minor points. So diagram on the left here, the grey circle relates to the bar, that's the handlebar, this is a cross section through the handlebar, and on the left is the stem opening. And you can see what I mean. The stem opening diameter is smaller than the diameter of the handlebar, so as you put the handlebar in, it pinches on the corners. And my friend who owns this bike was using a carbon fibre base bar, handlebar, and there's damage to the handlebar. Inexcusable shit. How the fuck can someone fuck it up so bad? I don't know. And that's not me doing fucking hand beanie Tourette's. This actually makes me angry too. Fuck's sakes. Right, number 7, which is the point about. What was number 7? Flawed UX. Okay, I'm trying to be like millennial and cool, because I put UX, which actually means user experience, which is spelt wrong because then it'd be UE and it's all fucked. Anyway, if the user does up the bolts first on the bar, the slipping may be worse. Okay, so what do I mean? If the user does the bolts up on the faceplate here, where the pointer is, and then by accident sets them wider, or because of clearances in the bolts and the through holes in the faceplate, it's possible that then there's clearance down here, but these are already fixed. So when you do up your N8 pinch bolt, you have to use some of the loading from the bolt to actually fucking bend this thing into before it even touches the bike. And you've already gone through maybe, I don't know, a kilonewton of your tensile load just using up to do that. And then when that contacts that, it won't be flat, it'll be bent. So you've only got like a line contact on the bottom here. Again, that's what I'm saying, user experience is bad, it's not user friendly. I don't even know if UX is the right term, but anyway, fuck. It's not user friendly because there's a lot of potential to fuck that up in something so simple. And they don't tell you, do this bolt up first and then bolt the faceplate on. If it had to be done like this, I would say in the user manual, do this bolt up first, but I'm not aware of it, and it's just, you shouldn't even have to put that in your user manual. If you do have to say something like that, it's design wrong, it's a design issue. Moving on. Number 5, more unrivaled dipshittery from the manufacturer. And the clue is in this fucking massive picture here. Ignore this bit, this is a bit I 3D printed, that's not the broken bit, I just 3D printed a part of the new design. Anyway, can you see what is down here? Serrated washers. Fuck me. So, my mate who gave me this bike, before he asked me to fucking sort it out, he got back to look and said, come on, I've had this stem for ages, I've had this bike for ages, I can't stop the stem slipping, can you help me out? And what do? They made him buy, I believe, these serrated washers. And what has that done? Well, that's dropped the friction coefficient from pretty low to fucking nothing, because now he's basically trying to clamp a flat surface with all these tiny points, these tiny line contacts. Now, for serrated washers to work, or index washers to work, they have to have corresponding fixed teeth positions on the mating part. So you'd have to have a serrated surface on here, on the stem plate, and a serrated surface on the bike to lock into, and then they can kind of work, but they're not backlash free and they're not great. So the parts don't have the mating faces, which are serrated, so you're basically mating the flat plates onto these tiny little ridges which are just flat and fucking slippery and doing nothing. So that decreased the clamping torque. It decreased the friction of the clamp even more. And because basically in this scenario the friction coefficient is directly proportional to the slipping torque of the stem. So let's say you've got aluminium on steel or aluminium on aluminium. Friction coefficient is not bad depending on the machine surface, but then what they've gone and done is reduce that even more by using these dumb fucking washers, which aren't right for this application. So what did he do then? Well, because the friction went down, he then had to do the M8 pinch bolt up even more to try and get the friction loading back up, and they made the problem worse, because eventually that's when he snapped the part under the bolt head in tensile loading, was when he had these serrated washers, because he had to put so much torque on the bolt. The tensile loading through the bolt was so high it broke the stem. So let's look at how we fixed it. And before I get into this, this is not by no means a redesign. This is something to get him back on the road, and we made a few improvements. The whole design and assembly is flawed. It needs a complete new front end. And I did say to him, like, I can make you a new one, I can try and make it a little bit better, but actually it's still not perfect. And I expect the other side, so there's two face plates here. I made him a new one for the part that snapped, and I didn't replace the other one. I said, mate, it's only a matter of time before the other part, which is actually the threaded part, before that fails as well. And I said, just be careful, because it's still a flawed design. Anyway, let's go to the 2D and look what happened. So we come out of that 2D drawing. We'll come to that in a minute. Where's the other part? So this is the engineering drawing of the, how do I do full screen, full screen, full screen? Control L, someone could have told me that. Basically, top level, so what do we do first? Change the material from 6061 to 7075 T6. Now 7075 is the same density, more or less, same material properties, same stiffness, but its tensile strength is a lot higher, which is also good for threaded parts. Like, you shouldn't really thread 6061 T6 because it's soft as shite. Always thread 7075. Did some basic kind of machining to take out a bit of weight because the old one was really heavy. And then another basic thing we fixed was the bar opening diameter. The minimum tolerance of that is still going to be larger than the handlebar, so there's no way the corners are going to pinch. I also put a chamfer on the corner as well, because it's no good having a sharp edge there. It's just potential for damage. Put a chamfer all the way around the bar clamp actually, and actually this is amazing how many high-end stems you see on the market with sharp edges. You never ever have a clamp with a sharp edge because it will fret and damage the part, and it's especially bad if you're using carbon handlebars, because if they get fretted or pinched or done by a corner, you know, potential is really nasty damage there. And I've got a really high-end zip stem in the other room, which I used on a physique handlebar, a carbon handlebar, and it fucking damaged it. It was sharp, and just the fretting from loading the handlebar in the corners of the stem clamp damaged it. Anyway, moving on to the bigger things. This counterbore for the M8 bolt. So right, the M8 bolt sits in here and goes through this through hole, and it's a counterbore. In the original design, this bottom surface of the counterbore was in line with this face, so there was a very, very thin next portion, which is where the stress got so high, and this is where the failure occurred. It cracked across here. Well, the tensile failure occurred across here because there was so little material under the bolt head, and all this is tensile loaded. This middle portion is tensile loaded to the threaded bit on the other side, and it cracked across here. So I actually reduced the size of the counterbore to lift this face up to give much more. I've doubled the thickness of material through here. So in that zone, the stress is halved because I've doubled the thickness of material. I've also added quite a modest radius in here and a radius in here, and that, like I said, is to reduce the stress raising effect of the corner. The original one didn't have any radius in the corners. It was just cutter had come down, the milling machine cut a corner out, and that's probably where the crack or failure initiated or propagated from. Was that corner, and that's like fucking year one shit, mate, engineering school. Yeah, anyway, yeah, so put chamfers everywhere, lots of radiuses, radius on the outside, and yeah, still not perfect. Still not perfect because it's a flawed design and it still can rotate. Still a flawed design, but I had one little extra trick up my sleeve to stop the rotation. How could we increase the clamping friction of the single M8 bolt? Well, originally, as you saw, it was supplied with serrated washers which were doing nothing. They were just making it worse. Now, I made these two very thin compliant aluminium washers with a grit blasted finish. Now, I asked the supplier to use a very high pressure and a very hard alumina particle to grit blast the surface of these washers. Now, what does that do? Well, it peens, shot peening or air abrading or grit blasting, sandblasting. It deforms the surface of the part and it actually yields it, and then what it does is it's what's called work hardening, and the part in that local area actually gets harder and more resistant to more resistant to wear and surface damage. And if you use the right size particle, you can make these very high friction washers. And I've used these in clamped arrangements before, and they can actually increase the friction coefficient by twofold. And so I specified that, and I think I've got some pictures of the finished piece here. So this is the finished plate, one side of the plate. You can see the radius is there underneath the bolt head. Nice chamfer on the bar opening there. Still pretty crude, but you know, I'm stuck with what I had to start with. And then this is it installed on the bike. You can see it's a pretty old TT bike. The picture there. And here are the two high friction washers, which have got this very fine abraded surface, which is very hard. And it's such a fine grip that it really digs into this material and this part here, and it keys both surfaces together, and it provides like a very arguably backlash free friction face. And actually we couldn't get the thing to slip now, and we were doing this up to 8 Newton meters, doing the M8 bolt up to 8 Newton meters, which is, you know, pretty modest for an M8. It's pretty low, and we couldn't get the thing to slip with our full body weight really jumping on it, so kind of 2 times 2G body weight or something like that. Now you can see, you might say, oh look, your counterbore, the M8 bolt is sticking out the counterbore. Well, that's as per design, because like I said, going back to the engineering drawing, I wanted to increase this thickness here and get this neck region away from this face, just to increase the amount of material under that dart to reduce the stress. So having the M8 out, sticking out a little bit into the wind is is not a bad thing, trust me, because it's a lot safer like this. And if you were being really picky, you could pick a low what's called a cheese head screw to be lower. And that's it. It's still not perfect design. I still didn't make the other half because I said, you know, I wanted to prove it to him that it will fail again, and then when it fails again, if he's not in A&E or at the dentist, I'll make him the other part. Anyway, so where's the PowerPoint gone? Oh, we saved a bit of maths, don't know if I mentioned that yet. So if you enjoyed this kind of thing, I'm sorry about the lighting, it's getting darker and darker, it was a bit of a long video. If you enjoyed that kind of thing, let me know. I've not done one of these videos before, these kind of design videos. And yeah, leave a comment down below, subscribe if you haven't already, do all that rubbish, and cheers for coming.